It's time to start playing around with Pascal's triangle. This is a pattern that if you decided to take stats next year, you are going to get very, very familiar with very quickly. This is a pattern of numbers. It's not too difficult to create. All of the outside numbers in this pattern are going to be 1. So that's where all these ones are coming from, as well as those ones. And we can continue those ones down the diagonal forever and ever and ever until you run out of time or your computer runs out of memory. To get all the inside numbers, well, getting the inside numbers is just adding the two numbers diagonally above it, which is weird to say out loud, but in practice just means I'm going to take this 1 and this 3, and their sum will go in that box. So 1 plus 3 is 4. I can continue doing that to fill in every blank. 3 plus 3 is 6. 3 plus 1 is 4. And then jumping down to the next row, 1 plus 4 is 5, and so on. 4 plus 6, 10. Another 10, and another 5. Now, we only have 5 rows on these notes, but you could do this forever. I mean, I could take the 10 and the 10 and get a 20. Flanking either side of the 20 would be a 15 and a 15, coming from 5 plus 10. But of course, you wouldn't want to make 80 rows of this thing. So if you just Google Pascal's triangle, you can find somebody who has made one of these things huge. And if you're really feeling up to it, you could program this in a computer very quickly and get thousands and thousands of rows of Pascal's triangle. So the reason we care about this pattern is that a lot of things show up using these numbers. My personal favorite, because of the computer science background, is all the powers of 2 that we get. If you look at the sums of each row, well, you can't add anything to that one. That's just 2 to the 0 power, which is 1. But everywhere after that, 1 plus 1 is 2, and that's the same as 2 to the first power. 1 plus 2 plus 1 is 4. That's the same thing as 2 squared. 1 plus 3 plus 3 plus 1, that's 2 to the third, which is 8. The next sum will be 16, then 32, and so on and so forth. So that's one of the patterns that I personally enjoy, although it's not going to be that interesting for us in pre-calc. Some other patterns that show up, if you look down the diagonals, you can see the natural numbers, which is a fancy way of just saying counting numbers, 1, 2, 3, 4, 5, 6. The next row is the triangular numbers, which if you're looking at the pattern there, plus 2, plus 3, plus 4, plus 5. So there's a nice recursive pattern that you can get there in the triangular numbers. These other two are fancy, and I'll leave you to Google search those on your own. But there are tons of patterns that show up in this triangle that are useful to various different branches of mathematics. Also, conspiracy theorists, because, you know, they love things like the Fibonacci sequence. So here's the Illuminati coming back. It's weird to get the Fibonacci sequence. This color-coded picture does a great job of showing how to get it. But you're kind of moving like a chess piece to get these numbers. It's not quite the diagonals. It's the ones that don't quite touch one another. It's a weird diagonal. But if you follow that pattern all the way down, you get all of your Fibonacci numbers as well. So Pascal's triangle is hiding tons of fun little things here. For more nerdy observations, there's a website that I'm not even going to try to pronounce. Nope. So what we are going to use Pascal's triangle for, bringing things back to pre-calc, is talking about binomials. Binomials, again, is just two numbers together hanging out in parentheses. So if we were to take a binomial to the 0 power, well, anything to the 0 power is just 1. That's kind of boring. And if we were to take that binomial to the first power, well, anything to the first power is just itself. So that's boring. Where we start having to do a bit of work is higher powers, like squaring or cubing. Remember, squaring anything, well, that's the same as taking that binomial and multiplying it by itself. And that's a FOIL problem. A times A is A squared. A times B is BA, or AB if you want to keep things consistent. You got your inside terms, B times A, it's another AB. And last but not least, B times B is B squared. Again, we got that through FOIL. Combining some like terms and adding in those coefficients will give you 1a squared, 2 of those ab's, and 1 of those b squareds. We could do this by hand one more time without going too crazy. We could say a plus b cubed. Well, cubing something is just multiplying it by itself 3 times. So that would be 3 of these a plus b's. But we already know what 2 of them is. So really, this just becomes one of those obnoxious 3 by 2 foils, which I'm going to do at super speed. Kabam! So all of this talking and all these numbers, and we're like, oh, what the heck is he talking about? If we start looking at these coefficients, 1, and then a 1, 1, and then a 1, 2, 1, and then a 1, 3, 3, 1, we start to see that, that pattern we were just talking about shows up there as well. We can actually extend this quite a ways. We can get every set of coefficients for taking a binomial to a power from Pascal's triangle. Mathematically, we would say that they form the nth row of Pascal's triangle. I'm just bringing one of these triangles in here to explain what we mean by nth row. The 0 power matches up with the 0th row, the one there at the top. The first power matches up with the first row, and so on and so forth. Second power matches up with the second row. What's weird is that we do start counting at 0. Again, for those of you taking stats next year, get ready for that. That's going to happen to you a lot. But as long as you're willing to accept the starting, counting, and zeroing business, Pascal's triangle gives us all those lead coefficients for squaring that binomial a plus b. So this is a good place to stop with the intro stuff here. We're going to take a look at some patterns we notice, and then we'll stop. My fault. So if we take a look at just a handful of things that come out of that, the total number of terms is always the exponent plus 1. It's 1 more than the exponent. Remember, taking something to the 0 term gave us 1, so the 0 power gives you 1 term. When we took something to the first power, we got a plus b, so 2 terms, which is 1 more than 1. So there's always 1 more term than the exponent. The first term has that coefficient of 1, and the last term has that coefficient of 1. And then if we take a look at the actual exponents, going back here, clear off all this ink, if we take a look at those exponents, there's a pattern there as well. Probably easiest to see here in the 5th row. If we look at the exponents of a, they go 5, 4, 3, 2. We don't ever write the 1, but then that's 1. And then there isn't 1 at the very end, so that's a 0. If we look at the exponents of b, well, none, 1, 2, 3, 4, 5. So the exponents for our first term start at 5 and go down. The exponents for our second term start at 0 and then move up. So the exponent for a, the first term, decreases by 1. From left to right. So order does matter here. We're talking from left to right, just like reading. Whereas the exponent of b is going to increase by 1. Again, talking from left to right, just like reading. And so last but not least, one kind of final thing worth noticing is that if you were to add those two exponents together, they always equal n, the power that we are trying to raise this whole thing to. So note that here and here, it's just 5, which is the power that we cared about. But elsewhere, 3 and 2, well, 3 plus 2 is 5. We get the same thing here with 3 and 2. 3 plus 2 is 5. And then as you branch further outward, 4 and 1 is 5. 4 and 1 is 5. The exponents always add up to the power that we're raising the binomial to. And that happens anywhere, not just for 5. Note that 2 plus 2 is 4, 3 plus 1 is 4, 4 plus nothing is 4. So we get that pattern as well. The sum of the exponents will always be n. So using these rules, we can raise a binomial to a power very, very quickly, which we'll do in the next video. This one's already been way too long.